Let's do a slightly more involved example of stoichiometry with limiting reagents. And it's only slightly more involved in that we're using masses. And for stoichiometry, you have to use moles, so we'll have to do a little converting first. But the pattern of what I do will be the same. I'll start by writing, at the outset, a balanced chemical equation. Now, if we're reacting aluminum with oxygen, those would be my reactants. And anytime you react a metal with a nonmetal, the metal gets oxidized, the nonmetal gets reduced. We're going to get aluminum cations, we're going to get oxide anions, and our product's going to be aluminum oxide. We can balance this equation very simply with a 2, a 4, and a 3. So yes, for every 4 moles of aluminum used, we'll use 3 moles of oxygen, and we'll get 2 moles of aluminum oxide product. Now, remember how we calculated in the preceding example which the limiting reactant is. And I know it's a limiting reactant situation because I have amounts of 2 or more, in this case 2, of the reactants. And when you have 2 or more reactant amounts, it's highly unlikely that you'll have exactly the right amount for each to fully react, and that one is going to run out and be exhausted first. And when that one reactant runs out, it limits the reaction and the reaction stops. So to find our limiting reagent, we're going to first need moles, and 20.0 grams of aluminum at 27.0 grams per 1 mole, the molar mass of aluminum, means that we're beginning this reaction with 0.741 moles aluminum. In the case of the oxygen, at 20 grams, with a molar mass of 32 grams per mole for oxygen, twice the 16 atomic mass units of oxygen, masses cancel, and we know we're starting with 0.625 moles of oxygen. Now, yes, we are starting with more aluminum than we are with oxygen. We have more of these atoms than we have these molecules. But that doesn't mean that the oxygen runs out first and is limiting. And that's because, of course, we need different numbers of these two things. And it might well be that the aluminum is limiting. So the way I quickly check which is limiting once I have moles is divide each by its coefficient. Divide each by its coefficient. And when I do that, I get a ratio of 0.185 and 0.208 respectively. So what I'm doing is taking how much of each I have, and I'm adjusting them based on how much of each I need. And it turns out that I have less aluminum than I do oxygen for the purposes of this reaction. The smaller value is the one that's my limiting reagent. And I will use that limiting reagent to do my calculations from now on, all calculations, because that's the mass of aluminum that limits me, and there are 27 grams of aluminum per 1 mole. And now I can do the stoichiometry, because for every 4 moles of aluminum, I should produce, I want to know product, 2 moles of aluminum oxide. So 2 moles Al2O3 for every 4 moles Al. And now I have successfully converted from aluminum to aluminum oxide using the balanced equation. Of course, this does request a mass of product, so I have one more step, because 1 mole of aluminum oxide is 102 grams aluminum oxide, the molar mass of aluminum oxide, meaning we're going to get 37.8 grams aluminum oxide as our product. Now, we're going to do the second part of the problem the same way we did back in our previous examples. We want to know what mass of which reactant will be excess. And immediately when I hear excess, I think two things. What did I start with? I started with 20 grams, and my excess is going to be oxygen because aluminum was limiting. The other reactant is excess. And I take what I start with, and I'm going to subtract what I use. Now again, I don't automatically know what I'm going to use. I need to instead do a quick calculation, stoichiometry. And I always start with the limiting reagent in all parts of these problems involving limiting reagents. And 1 mole of aluminum is equivalent to 27 grams of aluminum. Have to use moles when I'm doing stoichiometry. And then the relationship between aluminum, the limiting reagent, and the excess reagent, oxygen, is 4:3. And there's my stoichiometry now, is that for every 3 moles O2 I had 4 moles of aluminum. That's how many moles of O2 I will use. But I can't subtract moles from mass. I have to convert back to a mass. And that's easy because 1 mole O2 is 32.0 grams O2. Meaning I use 17.8 grams O2 used. Remember my warning. This is not the answer. It's what I need to find the difference. Because if I start with 20 grams of oxygen and I use up 17.8 of it, turning it into product, it means I'm going to be left with 2.2 grams excess O2. Now that answer makes perfect sense because we started this reaction with 40 grams of mass total. I had 40 grams of aluminum and oxygen to begin with. And of course, law of conservation of mass tells me I should end up with 40 grams of matter after the reaction if I started with 40 grams of matter. But notice our product only contained 37.8 grams of matter. In other words, if I have 40 grams to start with and I end up with 37.8, it looks as if 2.2 grams of matter have disappeared. But they haven't. It's just unreacted O2 that's left over. 2.2 grams of excess. So that confirms my calculation of what I used. Now, as a final example, jazz it up a little bit. When 30 grams of butane is burned with 30 grams of oxygen, what mass of water is produced and what mass of which reactant is excess? Well, we start by writing the reaction and balancing it. Butane, C4H10, oxygen, O2, and we get carbon dioxide and water anytime we combust a hydrocarbon. And we can balance it pretty easily with a 2 and an 8 and a 20, or excuse me, a 10, and that means we need 13 oxygens. Now, we've got 30 grams of butane, one reactant, 30 grams of oxygen, the other reactant. Again, one of them has to run out first. Our first goal always is to calculate who's limiting. And I start by comparing moles. Masses don't tell me. Moles will. And since 1 mole of butane is the equivalent of 58 grams, hence the molar mass of butane, this is how many moles of butane I start with. And same is true of oxygen. If I start with 30 grams, it has a different molar mass. A mole of oxygen is equivalent to 32 grams of oxygen. It means I start the reaction with 0.517 moles of butane, roughly, and with 0.938 moles of oxygen. Now, when you do this, again, I have to remind you that first-year students tend to make a dreadful mistake. They tend to say, oh, I have fewer moles of butane than oxygen, it's going to run out first. But remember, this doesn't account for the fact we need over 6 times more molecules of oxygen than molecules of butane for this reaction. So that's why we take the coefficients of each and divide the number of moles by their coefficients to get the relative values, in this case, of 0.259 and 0.072. Now remember, when you do this, these numbers have no meaning other than to let me eyeball who's going to run out first. And since the smaller value belongs to oxygen, because we do need 6.5 times more of it than the butane, always take the smallest value when you do this procedure, and that's your limiting reagent. So every calculation I'll do will be based on my limiting reagent. So we want to know what mass of water is produced. Well, I know for every 13 moles of oxygen, we'll get 10 moles of water. So I do the stoichiometry based on my limiting reagent, because the oxygen will, in fact, run out first. 1 mole O2, 32 grams O2. And now the stoichiometry. For every 13 moles of O2, we get 10 moles of water. So 10 moles water for every 13 moles O2 used. That's how much product I'm going to get. But since it wants a mass, I know the molar mass of water is 18 grams per 1 mole. And I will have my answer. With 30 grams of oxygen, we're able to produce essentially 13.0 grams of water by this process, so stated. Now remember, how do you find excess? You always need two things: the amount you start with and what you use. Now my excess in this case will be the butane, because the oxygen is the limiting reagent. And I know that I start with 30 grams, so all I have to do is calculate how much I use. And I will base the calculation on my limiting reagent. For every 13 moles of O2, I also use 2 moles of butane. So a quick calculation: 30 grams of oxygen. Need moles if you're going to play with stoichiometry. 1 mole of O2, 32 grams O2. Now for the stoichiometry. We're going to use 2 moles of our butane for every 13 moles of O2 that we use. So that's how much butane we have to use. But of course, I can't find the difference between 30 grams and so many moles, so I need grams of butane, a mass of butane. And 1 mole of butane is 58.0 grams of butane. Meaning, and this is used, don't forget, it's the other reactant, it means we're going to use 8.37 grams of our butane. And now I can get my final answer, because I started with 30 grams of butane and I used up 8.37 grams of butane. And with the correct significant figures, it means I get 21.6 grams of butane excess. There's the answer. So now, to summarize, anytime you have more than one reactant amount given to you, it's a limiting reagent situation. And then when you know it's a limiting reagent situation, your first goal is to find the limiting reagent. You do that by using moles, dividing each by its coefficient and comparing to see who's the smallest value. That's your limiting reagent. Once you know your limiting reagent, you start all parts of the problem with it. You use it to calculate how much of a product you can get, because once you run out of limiting reagent, you stop making product. But you also use it to tell you how much of the other reactant you use. And you can get excess by subtracting what you start with what you use.